In this video, I'm going to be talking about interpreting motion graphs, such as distance time graphs, velocity time graphs, and acceleration time graphs. This is part of topic 2.1, which is in the SL and HL sections of the IB Physics Syllabus. Please take a moment to read the success criteria for this video. Okay, so let's start off by talking about distance time graphs. Now, first of all, I want you to look, and I have an S there versus T. And no, that's not a mistake. We're going to use S. And some people would say S would then stand for its position rather than distance. But you can think of it as distance from the origin. So it's a spot. Now, in all these cases, I'm going to be talking about moving in a straight line, forwards or backwards. So if I'm moving in a forwards direction, let's call that to the right, I would say I'm at a positive position from the origin. So you can see up above, I've got a little distance timeline here. And so if I was at the origin right here, if I wanted to move in the positive direction, so I'm going to say to the right, I can move all the way over to here, and now my S would be a positive value. Likewise, if I'm on this side, my S is going to be a negative value. One other word you're going to hear is displacement. Now, displacement is the vector interpretation of distance. It means what is the distance with a direction from where I started to where I finished. Sometimes we say that's as the crow flies, because a bird wouldn't stop to walk in all the different directions. It's just going to go straight from the beginning to the end. Okay, so down below I have a distance time graph. So let's walk through what it's actually telling me. Now, at the beginning, you can see that my S is positive, so I must be starting at some kind of position over here. And let's see, what does it do at the beginning? Well, as time progresses, its position stays the same. Well, here we go. Ready? Let's say this horizontal line happens for 1 second. And here's my star, here's what's going on. And for the first second, it does just that. A horizontal line on a distance time graph means our object is not moving. But now let's look at this second spot here. Let's first think about what is happening according to my distance time graph. On my graph, I have a negative gradient. What is that going to mean for my star? It's going to go from here, and then it's going to go to this spot, which is just my origin. So my first second, here we go. And then my second section, it's going to move to the origin. Okay, so let's see what that meant. It's moving to the origin, and it's taking the same amount of time to go across until eventually I get here, and we know what that happens. That means I stop at that point. But in this section here, what direction was it going? That's right, it was going in the negative direction. Started here because S was positive, and it went to the origin. If it's moving in a negative direction, that means it had a negative speed. Well, actually, no, a negative velocity, because this is using direction, so we have to use the vector. And because my line is a straight line, that means it was going at a constant velocity. So you can see I've written on the distance time graph the different pieces that we've done so far. Okay, so we've got our little star. It started at a positive position. It moved in a negative direction at a constant speed until it got to the origin. And then now we're at this spot right here. So take a second and think what's going to happen to my green star. Well, I hope you said that it was going to continue to travel in the negative direction, and it's going to continue traveling at a constant negative velocity. And I know it should be the same constant negative velocity because it has the same steepness of the line. Both of these places have the same steepness. Okay, so it's probably going to go about that far. Now, how do I know that? Well, take a look. We had this much in the positive direction when it started, and now it's this much in the negative direction past my origin once we're there. We've got one last thing that's slightly different. Right here, we have that it's there, but look at it changes just slightly. We no longer have a straight line. What do you think that means? Well, I hope you realize this is going to be acceleration. If you notice, the gradient or the steepness of that line is constantly changing, which means its velocity is going to be changing. Now, positive velocity or negative velocity? Positive velocity. And I hope you realize that because what's going to happen to my little star? It's going to be moving in the positive direction. Okay? Yes, it's starting off in a negative position, but velocity is all about which direction it's going. So it's starting down here, but it's going to move towards the right. So it's going to slowly at first and then quickly increase. It is going to be having a positive velocity. And because it's changing, we're going to say that that's acceleration. Okay, so let's just recap this before we go on to the next graph. Most people have seen distance time graphs before they start IB physics, but this is just to make sure we've covered all the bases. If we have a horizontal line in a distance time graph, that means my object's at rest or stationary. If it's moving and I have a constant gradient or a straight line on an angle, then that means I must have a velocity. I am moving. And if it's a straight line, then that velocity will be constant. If, though, my line is curved, that tells me my velocity is changing and I have acceleration. So on a distance time graph, a gradient indicates velocity. Okay, so let's move on to velocity time graphs. And remember, this would be better to say velocity time graphs than speed time graphs because we are talking about direction. Just remember, a positive velocity means it's moving in a positive direction. A negative velocity means it's moving in a negative direction. It doesn't tell us anything about where it starts, only which direction it's moving. So I could begin this by having my little green star anywhere along here, and it would still work and give me the same velocity time graph. If I want you to know where it started in reference to the origin, I have to give you some more details than just a velocity time graph. All right, so let's start with my green star right here for a moment. Now, if we look on our velocity time graph, for the first section, you can see that my velocity here is 0. So what does that mean? That's right, it's stationary, it's at rest, it's not moving at all. But in this first part here, you can see that its velocity is going to go from 0 and it's going to increase in velocity to a certain value. Now, these are all positive velocities, so that means it must be moving in a positive direction. I.e., in my blue diagram above, that means to the right. So if it's going to start at rest, but then increase its speed, what does that mean? That's right, it's going to accelerate. Now notice this is going to be positive acceleration because we have a positive gradient. More on that a little bit later. Once I get to the top here of my line, you can see that my velocity is always the same. What does that mean? That's going to be a constant positive velocity. Positive in this case because I'm above the x origin. Okay, so it's at rest. It's sped up to a constant velocity. And then now take a look. We have a constant velocity and it's going to slow down. And right here, it's going to stop. Now, I want to really point this out and emphasize this because a lot of the times students come into my IB physics class and they've been taught that deceleration means negative acceleration. And what we've done so far, that would be true. My negative gradient here is slowing down, but, and there usually is a but. In those cases, your teacher would have always had you only going in a positive direction. So in fact, slowing down in a positive direction gives me negative acceleration. Take a look what I had in the first part. In this part, I have speeding up in a positive direction, giving me positive acceleration. Let me write that down. So speeding up in a positive direction, positive acceleration. Slowing down in a negative direction, negative acceleration. Here's a good also time for me to point out that the word deceleration is not a science word. It's an everyday English word that means slowing down. Okay, so in our examples, we may still use the word deceleration. It's the same calculation, but it doesn't always have to be a negative number. It only implies slowing down. So let's take a look at my graph again. Because I've got this slowing down and stopped, and notice that my gradient isn't changing here at all. In fact, once I've got it stopped, I have it now. Well, the magnitude of these numbers, of these velocities, are getting greater. It just so happens that these are all negative, which means it's now speeding up because the magnitude's getting bigger, but in a negative direction. So look what's happened. When your line crosses the x-axis, it actually is going to change direction because we've said before that if my velocity is positive, it's moving in a positive direction. But if my velocity is negative, it's moving in the negative direction. So in fact, if I want to move my little green star, here we are at first, it's stationary. It's going to speed up in a positive direction and then travel at a constant speed, slow down, stop, and then speed up and move in the opposite direction. One thing to point out is that this part here is actually the diagram you get when you throw something up into the air. When you release it from your hand, you know that it's traveling at a certain speed. And as it goes up to the top, at the very top, it stops. Remember, it's working against gravity. Gravity, the acceleration due to gravity is going to be negative 9.81 meters per second. So if I don't have any air resistance, the gradient of this line here would be 9.8. Once I get up to the top, what does it do? It turns around and starts falling down and speeding up back towards my hand. Okay, so let's think what we've got here then. If I was speeding up, like I have right here in my graph, in a negative direction, that is giving me negative acceleration. My gradient on the velocity time graph is negative. If I continued this red line here up back to the x-axis, I would then have it being slowing down in a negative direction, because remember this is a negative velocity. And notice how my gradient now is positive, which would give me a positive acceleration. Here's how I remember it. Two positives make a positive. So speeding up in my mind is positive. Positive direction, I get positive acceleration. Slowing down in my mind is that's negative. Slowing down in a positive direction, negative, positive, that gives me negative acceleration. So now in the negative direction, if I'm speeding up, negative and positive gives me positive, sorry, negative and positive give me a negative acceleration. And then at the end, slowing down is negative. It's a negative direction. Two negatives make the positive acceleration. One last thing I'm going to point out is we're almost always going to have velocity time graphs that have straight lines on them. That would imply that our acceleration is uniform or constant. There are a couple examples when we don't do that in the course. They're usually involving simple harmonic motion. But if it's not simple harmonic motion, we will expect to see straight lines. One last thing that we can do in velocity graphs is to find out the distance traveled. So we've just been talking about how acceleration would give us the gradient. How am I going to find out how far I've gone? Well, one part, if we think about it right here, when we were traveling at a constant speed, we know the equation for a constant speed. We could use the equation v equals d over t, d being the I purposely am not using the letter S so that we know that we're not talking about acceleration here. Now, if I move that around, my distance would be my velocity times my speed. Now, notice what I've marked on the diagram. If I have it here, this is my time, and this height is my speed. So, in fact, if I want to get that, that's the area of the rectangle that I've just shown. And that's really how I get distance from my velocity time graphs. It's the area under the line. Now, I've started off with this really easy one because that was traveling at a constant speed, and I know the easy constant speed formula. If I want to know that total distance it's traveled from the beginning here to this part at the end where it stops, then I will need the total area. Now, here's the thing. You're just going to be able to break that up into pieces. I see two triangles and one rectangle. Some of you may have memorized the area of a trapezium or a trapezoid. Great. But you know what? I never remember that one. So I'll break it up into the pieces. If this line was curved, then I could, count the number of boxes inside and know the area of the box. But take a look at the number of marks. Typically, this would only be maybe 2 marks. And so you should be able to do that then, find the area in 3 minutes. So you kind of have to look at the mark scheme to see how accurate you need to be. In most cases, I would say break them into rectangles and triangles and you will be fine. Now, one other thing. This first part here was all moving in the positive velocity, moving in the positive direction. So that entire section there was moving to the right according to my number line at the top. If we look over at the next part here, all of this was moving with the negative velocity. So it's moving to the left in the negative direction. And again, I could calculate that. That looks like a nice little triangle. And in this case, if I subtract the two, I will find out how far I am from where I started. I went all this yellow distance here to the right, and then I backtracked and went only this far backwards. And you can see by just glancing at the areas I've drawn that I have not got back to where I started from. I've only made it way partially back. Okay, so if we were in simple harmonic motion, we could see an acceleration time graph looking something like this. And you'll see more simple harmonic motion in topic 9, especially from HL students. And you'll also see it in topic 4 as well, where we'll do more of a qualitative for the SL students. We can see here that we've got acceleration is going to be 0 to a maximum. We can see that it's constantly changing gradient, so that means we are going to be having it changing over time. One important thing about any of that means no suvat. If you don't know what I mean by suvat, I mean the equations involving distance, initial speed, final speed, acceleration, and time that we use in topic 2. So many of the times we'll see a graph like this, and what it's implying is that right here we have no acceleration, Here we have a constant acceleration. Notice this vertical line means it's instantly gone from having no acceleration to having some. So the idea being from there was no force applied to instantly a force was being applied. Is it realistic to assume that? No, but in the order of simplicity, sometimes we'll assume that the force was applied basically instantaneously. So one of the things that I think would be a really good idea is if you take this and we go through what the different graphs mean. So let's take a look first at the horizontal line. On a distance time graph, that meant it was stationary. But a velocity time graph means constant speed. A straight line then, and I mean non-horizontal, would imply a constant speed. And depending on whether it's a positive gradient or a negative gradient, I could then get my velocity from that. Well, on a velocity time graph, that's going to imply acceleration, a uniform acceleration. A curved line on a distance time graph, that means acceleration. While on a velocity time graph means non-uniform or non-constant acceleration. If I cross the x-axis on a distance time graph, that means I pass my origin. On a velocity time graph, I have no idea where I started, but crossing the x-axis means something different. It means I've changed direction. So what I would suggest is that you also make yourself a table that looks like this, but instead of having the features of the line, you actually have a graph or table that says what you should graph in order to find it. For example, at rest, constant speed, acceleration, or change in direction. I'll leave that for you to do. It's a really good exercise to see whether or not you truly understand how to interpret your motion graphs. So please take a moment to read the success criteria again for this video. I hope it's helped you out.